Hello everyone, my name is Lan. Welcome to my presentation. I'm going to talk about our recent work called Faithful Euclidean Distance Field from Log-Gaussian process implicit surfaces. In this work, we propose a continuous and probabilistic mapping approach for multipurposes, suitable both for mapping and path planning. I will call it Log-GPS in this talk. Autonomous robots in unknown and unstructured environments require accurate representations of the world. These representations can be used for different purposes. For instance, recovering a high-quality surface reconstruction for mapping purposes requires dense, accurate, and high-resolution representation. On the other hand, navigation purpose requires an efficient collision checking with distance and direction to the nearest obstacles for local or global path planning. However, it is difficult to have both representations for mapping and navigation directly. In the literature, the discrete and combination methods are often required to propagate the distance through a grid. In this paper, we aim to solve this problem with a unified representation for mapping and navigation purposes. Our work, Log-GPS, is based on Gaussian process implicit surfaces. GPS combines both notions of Gaussian process and implicit surfaces in a continuous probabilistic representation of the 3D surface. It can represent the uncertainty and integrate nicely to fusion. We can use GP to formulate implicit surfaces with gradients. It allows estimating the value of an unknown function f at an arbitrary quarry point. The measurements will be some noisy 3D points roughly on the surface equal to 0. Also, we'll use gradients to tell the inside and outside. The famous predictive mean and variance at an arbitrary testing points will be given. In the literature, most standard GPS techniques can estimate the continuous implicit surface and the distance field of the surface. As we can see from Figure A, it's a continuous mapping using GPS. The green points are the measurements roughly on the surface, and the blue area is the inside distance field. Yellow area is outside distance field. Figure B shows that with the same data, conventional grid mapping approach often suffers from discretization errors and disconnected cells to reconstruct the surface. However, as we can see from this figure, GPS produces a continuous surface and good Euclidean distance field near the surface. But the distance information is not accurate far away from the surface due to the lack of training points. For example, using a zero mean GP implies that the prediction will include false positive artifacts, and the predicted function value falls back to 0. Our work addresses this issue by faithfully modeling a fundamental property of the Euclidean distance fields, inspired by the heat method. Before digging into more details, I will give an overall impression of Log-GPS. With point clouds and pulses as inputs for our framework, the outputs of Log-GPS provide surface normals, distance, and gradients of distance. Besides, all the outputs also have uncertainty information to show if the data is reliable. Inspired by the recently proposed heat method, it simply solves the regularized unkernel equation to model the distance field mathematically. By doing that, it can provide different information for different applications. Only minor modifications to standard probabilistic method. The computation time allows online operations. So here are some background knowledge about Euclidean distance and unkernel equation. Consider a manifold S in d dimensions with boundary partial S. The orientation is given by the normal n. For all x in d dimensions, we can denote the Euclidean distance field as dx, which means the closest distance to the boundary partial S. I will call it EDF if we talk about the whole field. Consider the boundary partial S moves in the normal directions with unit speed, then the arrival time will be equal to the distance dx. This intuition is captured by the unkernel equation. If we want to have the EDF mathematically, we have to solve the internal equation. The aim of this paper is using sparse measurements of the points on the surface to reconstruct the surface, partial S, and also to estimate the distance field. So how the log GPS works? As we mentioned before, only minor changes for GPS can achieve log GPS. Given a set of measurement points roughly on the surface, the target value of those measurement points set as 1. Then compute the GP inference result at the query point. After we have the inference result, simply take the logarithm of inference result to produce accurate distance. That's it. In the following 2 slides, I will talk about the derivation of log GPS. As we mentioned before, we can solve a kernel equation to recover the EDF, but it's difficult to solve it directly because it's nonlinear. We can solve a different equation which is linear regarding to Vx, and Vx is a transformation of dx. After we solve GP with Vx, we will recover the dx at the end. How to do it? A work in the computer graphic introduces a heat equation regarding to heat kernel to get around of solving a kernel equation. The heat kernel Vx and the EDF dx on the manifold are related as the Varidan's formula. There is a figure to show the physical intuition about Varidan's formula. Imagine using a hot needle to touch a point on this bunny. Over time, heat will spread out the rest of the domain, and this heat conduction can be modeled by the heat kernel Vx. Varidan's formula recovered the EDF on the manifold using the heat kernel Vx. So we find the relationship between dx and Vx. Instead of solving a kernel equation regarding to dx, we will solve Varidan's formula regarding to Vx. Also, the approximation gets better as t approaches to 0. We define the approximation of dx as ux. For log GPS, the distance at the query point is obtained by taking the logarithm of the GP inference result with target measurement set as 1. Varidan's formula replaces the nonlinear constraint on dx with a linear one on Vx, which we can easily incorporate into GP regression. We can rewrite the heat equation as below, where the W is wet noise. Then we can derive a covariance function for Gaussian process implicit surfaces. This covariance will automatically meet the distance constraint. It is precisely the Whittle covariance function, a special case of the Maton family with epsilon equals to 1. Here are some practical considerations of log GPS. When lambda is set to a large value, t gets closer to 0. It will produce a better distance approximation as we mentioned before. As shown in the left figure, relatively large lambda values will produce a more accurate EDF. However, t cannot be exactly 0. As a trade-off, we use lambda equals 40 in our experiments. Also, hyperparameter optimization is not considered because lambda is exactly the hyperparameter of the Whittle covariance, and t provides the necessary intuition to choose a good lambda value for the EDF inference. Maton family are epsilon minus 1 times differentiable. The Whittle covariance is 0 time differentiable. This means it cannot be used for GPS gradient inferences. The Whittle covariance is a special case of the Maton covariance family, and Maton epsilon equals 1.5 is once differentiable, which is more suitable for distance estimation with gradients. We propose to use the Maton version as a trade-off for extra information. In the following slides, I will show the performance of log GPS in 3 scenarios. First, the comparison of the true distance value on a simulated 2D dataset with laser observations. Then, we quantitatively evaluate the results in a 3D structure simulated in a gazebo simulation. Finally, in order to demonstrate the performance of all algorithms on a real dataset, we provide a quantitative and qualitative evaluation on a public available dataset. For all experiments, we represent 2D surfaces with continuous line and 3D surfaces as meshes. For 2D results, we compare our method with TSDF, standard GPS without log tricks, called GPS SDF. The subfigures at the bottom show the distance field along the cross line. It is obvious that in the last figure, the EDF is linear and accurately predicted even far away from the surface measurements. Our approach does not contain sign distance information. However, we recover the sign of the log GPS by comparing the predicted gradient of each testing point with sensor position. If the gradient is in the opposite direction of the sensor, we flip the sign of the distance value of the testing point. Then is the distance results in 3D simulated data. We compare log GPS with GPS SDF and VoxBlocks, a mapping approach proposed by ETH. The dataset consists of a pile of boxes simulated in gazebo. A cross-section of the simulated environment illustrates the distance values. At the quantitative measure, we compute the root mean square error for all the approaches. Our method produces the most accurate distance estimation. Also, we evaluate the quality of the surface mesh using the same benchmarks as for the distance field. For the reconstruction, GPS SDF and log GPS will produce nearly identical results, so we only compare with VoxBlocks. VoxBlocks and log GPS produce high-quality reconstructions, but ours can also provide uncertainty information, a gray area with high variance. The median computation time per frame of VoxBlocks is 1.5 seconds. Our log GPS consumes a median of 4.5 seconds, which allows online operations. Note that our method can only evaluate a horizontal line to save more time for collision checking for navigation purposes. The median time is reduced to 3.2 seconds. We use the same benchmark in a more challenging scenario with a real dataset. The real-world experiment is based on the publicly available dataset called an Lady dataset. Again, the proposed log GPS produces the most accurate distance field with the lowest root mean square error amongst VoxBlocks and GPS SDF. Finally, we present qualitative 3D reconstruction results for the real-world dataset. The surface reconstruction of VoxBlocks and log GPS is equivalent, but ours can also provide uncertainty information, a gray area with high variance. Here are two videos showing all log GPS reconstruction both for the simulated data and real-world dataset as I mentioned before. It shows that log GPS produces the most accurate results for the distance and comparable results for the surface reconstruction. It's ideal for both mapping and navigation purposes. Thank you for listening.